The thorium fuel cycle is a nuclear fuel cycle that uses the isotope of thorium-232Th as the fissile material. In the reactor, 232Th is transmuted into the fissile artificial uranium isotope 233, which is the nuclear fuel. Unlike natural uranium, natural thorium contains only trace amounts of fissile material, which are insufficient to initiate a nuclear chain reaction. Additional fissile material or another neutron source are necessary to initiate the fuel cycle. In a thorium-fueled reactor, 232Th absorbs neutrons eventually to produce 233U. This parallels the process in uranium breeder reactors whereby fertile 238U absorbs neutrons to form fissile 239Pu. Depending on the design of the reactor and fuel cycle, the generated 233U either fissions in situ or is chemically separated from the used nuclear fuel and formed into new nuclear fuel. The thorium fuel cycle claims several potential advantages over a uranium fuel cycle, including thorium's greater abundance, superior physical and nuclear properties, better resistance to nuclear weapons proliferation, and reduced plutonium and actinide production. History. Concerns about the limits of worldwide uranium resources motivated initial interest in the thorium fuel cycle. It was envisioned that as uranium reserves were depleted, thorium would supplement uranium as a fertile material. However, for most countries uranium was relatively abundant and research in thorium fuel cycles waned. A notable exception was India's three-stage nuclear power program. In the 21st century, thorium's potential for improving proliferation resistance and waste characteristics led to renewed interest in the thorium fuel cycle. At Oak Ridge National Laboratory in the 1960s, the Molten salt reactor experiment used 233U as the fissile fuel as an experiment to demonstrate a part of the molten salt breeder reactor that was designed to operate on the thorium fuel cycle. Molten salt reactor experiments assessed thorium's feasibility, using thorium fluoride dissolved in a molten salt fluid that eliminated the need to fabricate fuel elements. The MSR program was defunded in 1976 after its patron Alvin Weinberg was fired. In 2006, Carlo Rubbia proposed the concept of an energy amplifier or accelerator-driven system, which he saw as a novel and safe way to produce nuclear energy that exploited existing accelerator technologies. Rubbia's proposal offered the potential to incinerate high-activity nuclear waste and produce energy from natural thorium and depleted uranium. Kirk Sorensen, former NASA scientist and chief nuclear technologist at Teledyne Brown Engineering, has been a long-time promoter of thorium fuel cycle and particularly liquid fluoride thorium reactors. He first researched thorium reactors while working at NASA, while evaluating power plant designs suitable for lunar colonies. In 2006, Sorensen started EnergyFromThorium.com to promote and make information available about this technology. A 2011 MIT study concluded that, although there is little in the way of barriers to a thorium fuel cycle, with current or near-term light water reactor designs there is also little incentive for any significant market penetration to occur. As such, they conclude there is little chance of thorium cycles replacing conventional uranium cycles in the current nuclear power market, despite the potential benefits. Nuclear reactions with thorium. Thorium is like wet wood. It needs to be turned into fissile uranium just as wet wood needs to be dried in a furnace. Ratan Kumar Sinha, current chairman of the Atomic Energy Commission of India. In the thorium cycle, fuel is formed when 232Th captures a neutron to become 233Th. This normally emits an electron and an antineutrino by beta-decay to become 233 pascals. This then emits another electron and antineutrino by a second beta- decay to become 233U, the fuel. Fission product wastes. Nuclear fission produces radioactive fission products which can have half-lives from days to greater than 200,000 years. According to some toxicity studies, the thorium cycle can fully recycle actinide wastes and only emit fission products wastes. And after a few hundred years, the waste from a thorium reactor can be less toxic than the uranium ore that would have been used to produce low-enriched uranium fuel for a light water reactor of the same power. Other studies assume some actinide losses and find that actinide wastes dominate thorium cycle waste radioactivity at some future periods. Actinide wastes in a reactor. When a neutron hits a fissile atom, it either splits the nucleus or is captured and transmutes the atom. In the case of 233U, the transmutations tend to produce useful nuclear fuels rather than transuranic wastes. When 233U absorbs a neutron, it either fissions or becomes 234U. The chance of fissioning on absorption of a thermal neutron is about 92%. The capture-to-fission ratio of 233U, therefore, is about 1:12, which is better than the corresponding capture versus fission ratios of 235U, or 239Pu or 241Pu. The result is less transuranic waste than in a reactor using the uranium-plutonium fuel cycle. 234U, like most actinides with an even number of neutrons, is not fissile, but neutron capture produces fissile 235U. If the fissile isotope fails to fission on neutron capture, it produces 236U, 237 nepers, 238 Pu, and eventually fissile 239 Pu and heavier isotopes of plutonium. The 237 nepers can be removed and stored as waste or retained and transmuted to plutonium, where more of it fissions, while the remainder becomes 242 Pu. Then americium and curium, which in turn can be removed as waste or returned to reactors for further transmutation and fission. However, the 231 pascals formed via reactions with 232 Th, while not a transuranic waste, is a major contributor to the long-term radiotoxicity of spent nuclear fuel. Uranium-232 contamination. Uranium-232 is also formed in this process, via reactions between fast neutrons and 233U, 233 pascals, and 232 Th. The full decay chain, along with half-lives and relevant gamma energies, is 232U decays to 228, where it joins the decay chain of 232 Th. Thorium cycle fuels produce hard gamma emissions, which damage electronics, limiting their use in military bomb triggers. 232U cannot be chemically separated from 233U from used nuclear fuel. However, chemical separation of thorium from uranium removes the decay product 228 and the radiation from the rest of the decay chain, which gradually build up as 228 reaccumulates. The hard gamma emissions also create a radiological hazard which requires remote handling during reprocessing. Nuclear fuel. As a fertile material, thorium is similar to 238U, the major part of natural and depleted uranium. The thermal neutron absorption cross-section and resonance integral for 232 Th are about 3 times and 1/3 of the respective values for 238U. Advantage is thorium is estimated to be about 3 to 4 times more abundant than uranium in Earth's crust. Although present knowledge of reserves is limited, current demand for thorium has been satisfied as a byproduct of rare earth extraction from monazite sands. Although the thermal neutron fission cross-section of the resulting 233 U is comparable to 235 U and 239 Pu, it has a much lower capture cross-section than the latter two fissile isotopes, providing fewer non-fissile neutron absorptions and improved neutron economy. Finally, the ratio of neutrons released per neutron absorbed in 233 U is greater than 2 over a wide range of energies, including the thermal spectrum. As a result, thorium-based fuels can be the basis for a thermal breeder reactor. A breeding reactor in the uranium-plutonium cycle needs to use a fast neutron spectrum, because in the thermal spectrum 1 neutron absorbed by 239 Pu on average leads to less than 2 neutrons. Thorium-based fuels also display favorable physical and chemical properties that improve reactor and repository performance. Compared to the predominant reactor fuel, uranium dioxide, thorium dioxide has a higher melting point, higher thermal conductivity, and lower coefficient of thermal expansion. Thorium dioxide also exhibits greater chemical stability and, unlike uranium dioxide, does not further oxidize. Because the 233 U produced in thorium fuels is significantly contaminated with 232 U in proposed power reactor designs, thorium-based used nuclear fuel possesses inherent proliferation resistance. 232 U cannot be chemically separated from 233 U and has several decay products that emit high-energy gamma radiation. These high-energy photons are a radiological hazard that necessitate the use of remote handling of separated uranium and aid in the passive detection of such materials. The long-term radiological hazard of conventional uranium-based used nuclear fuel is dominated by plutonium and other minor actinides, after which long-lived fission products become significant contributors again. A single neutron capture in 238 U is sufficient to produce transuranic elements, whereas 5 captures are generally necessary to do so from 232 Th. 98 to 99% of thorium cycle fuel nuclei would fission at either 233 U or 235 U, so fewer long-lived transuranics are produced. Because of this, thorium is a potentially attractive alternative to uranium in mixed oxide fuels to minimize the generation of transuranics and maximize the destruction of plutonium. Disadvantages: there are several challenges to the application of thorium as a nuclear fuel, particularly for solid fuel reactors. Unlike uranium, natural thorium contains no fissile isotopes. Fissile material, generally 233 U, 235 U or plutonium, must be added to achieve criticality. This, along with the high sintering temperature necessary to make thorium dioxide fuel, complicates fuel fabrication. Oak Ridge National Laboratory experimented with thorium tetrafluoride as fuel in a molten salt reactor from 1964 to 1969, which was expected to be easier to process and separate from contaminants that slow or stop the chain reaction. In an open fuel cycle, higher burnup is necessary to achieve a favorable neutron economy. Although thorium dioxide performed well at burnups of 170,000 MWD-T and 150,000 MWD-T at Fort St. Vrain Generating Station and AVR respectively, challenges complicate achieving this in light water reactors, which compose the vast majority of existing power reactors. In a once-through thorium fuel cycle, the residual 233 U is a long-lived radioactive isotope in the waste. Another challenge associated with the thorium fuel cycle is the comparatively long interval over which 232 Th breeds to 233 U. The half-life of 233 pascals is about 27 days, which is an order of magnitude longer than the half-life of 239 nepers. As a result, substantial 233 pascals develops in thorium-based fuels. 233 pascals is a significant neutron absorber, and although it eventually breeds into fissile 235U, this requires 2 more neutron absorptions, which degrades neutron economy and increases the likelihood of transuranic production. Alternatively, if solid thorium is used in a closed fuel cycle in which 233U is recycled, remote handling is necessary for fuel fabrication because of the high radiation levels resulting from the decay products of 232U. This is also true of recycled thorium because of the presence of 228, which is part of the 232U decay sequence. Further, unlike proven uranium fuel recycling technology for thorium is only under development. Although the presence of 232U complicates matters, there are public documents showing that 233U has been used once in a nuclear weapon test. The United States tested a composite 233U plutonium bomb core in the Met Blast during Operation Teapot in 1955, though with much lower yield than expected. Though thorium-based fuels produce far less long-lived transuranics than uranium-based fuels, some long-lived actinide products constitute a long-term radiological impact, especially 231 pascals. Advocates for liquid core and molten salt reactors such as LFTRs claim that these technologies negate thorium's disadvantages present in solid-fueled reactors. As only 2 liquid core fluoride salt reactors have been built and neither have used thorium, it is hard to validate the exact benefits. Reactors. Thorium fuels have fueled several different reactor types, including light water reactors, heavy water reactors, high-temperature gas reactors, sodium-cooled fast reactors, and molten salt reactors. List of thorium-fueled reactors from IAEA TECDOC 1450. Thorium fuel cycle, potential benefits and challenges. Table 1. Thorium utilization in different experimental and power reactors. Additionally, Dresden 1 in the USA used thorium oxide corner rods.